Hello, in this video we will start covering Chapter 10. We are covering Chapter 10, Section 1, entitled Correlation. The key concept is introducing the linear correlation coefficient R, which helps tell us how well our paired data will fit in a straight line pattern. We will only be considering these straight line linear relationships, which means when we look at our scatter plot, everything should look like a straight line in either a positive or negative slope. The main idea is correlation. A correlation exists between two variables when one of the variables is somehow associated with the value of another variable. We will be concerning ourselves with linear correlations, one where the correlation exists in either a positively sloped straight line or a negatively sloped straight line. The strength of that linear correlation is told by the linear correlation coefficient R. R tells us how strong the linear correlation exists between the pairs of quantitative X values and Y values in our sample. Here we see some examples of scatter plots and their correlation coefficient R. In this first example, we see the data is positively correlated. It looks like the data is rising to the right, so the strength of our relationship R is a positive number. Looking at the second plot, we see that this data looks very linear but with a negative slope. And we see we have a correlation coefficient that is negative. This third scatter plot looks completely random, and so we would say this has no correlation. And we want to note the value being very close to 0. Now we can have other shapes. This is what we call a negative parabolic slope. Although this will be very correlated, this is outside the scope of this section, so we will not consider it. Our objective is to determine whether there is a linear correlation coefficient between two variables by computing the linear correlation coefficient R. But first, we need some notation. We have some new notation when dealing with calculating the linear correlation coefficient. N is the number of pairs of sample data. This big E looking thing is sigma. It denotes that we want the sum or addition of a bunch of items indicated. There are three main types of sums we will want to deal with. The sum of all the X values, the sum of all the squares of all the X values, and lastly, we may first want to sum all of the X values and then square that total. And that is what that last notation will be. What would be very important is distinguishing the difference between the sum of our x squareds and the square of our x's when we sum them up. We want to make sure that we understand the difference between those two. The last two new types of notation will be the sum of xy. This is indicating that we want to take each x value and multiply by its corresponding y value. Then, after finding all products, we compute their sum. And R will be the linear correlation coefficient for our sample data. If we have a population, there is a linear correlation for a population, although we will not be dealing with that in this section. Here we see the formula for R, our linear correlation coefficient. We don't want to get too bogged down at how difficult R looks, because there will be ways to compute R in a rather easy form. So just stick with it. When we compute R, we want to round R to 3 decimal places. There are some basic properties of R. One is that R will always fall between -1 and 1. If it falls closer to -1, that means we have a very strong negatively sloped correlation. If R falls very close to +1, that means we have a very strong positively sloped correlation. Second is that the values of either variable are converted to a different scale, right? Like from feet to miles, for example. The value of R will not change. Third, R, the value of it, is not affected by our choice of X or Y. We could switch our X and Y values, switch our axes, and the value of R will not change. Fourth, R measures the strength of a linear relationship. It will not measure a relationship that is not linear. Lastly, R is very sensitive to outliers, and so a single outlier could dramatically affect its value. So let's do an example. Here, we will use the formula we described to find the linear correlation coefficient R for the 5 pairs of data which correspond to chocolate intake of a country and Nobel laureates awarded. To solve this problem, like with many problems before, we will invoke the use of a table. We will put the chocolate as our x values, listing them vertically down, and the Nobel laureates as the y values, listing them down. We will then have 3 separate columns for squaring the x values, squaring the individual y values, and then multiplying the x and y value together. The last row will be reserved for computing the sum of each of these columns. And as we will see in the formula for R, a lot of these values and sums will be required. Here we have our formula for R. And what is nice about this is each of these sums is listed in the chart previously. Here we have these 5 pieces of paired data. If we look at all of these sums we have, we can bring them over to our formula and put them in the appropriate spots. If we plug in the value of n, the sum of xy's, the sum of x, the sum of y, and so on, we will get the second line. Computing each of the numerators and the square roots separately, in the third line, we can see that once we finish our calculation, we get a value for R of 0.795. So how do we interpret R? One way is to look at R squared actually, and that is going to be the proportion or percentage of the variation in Y that can be explained by its relationship with X. If we take our value of R and square it, we get 0.632. And so what does that mean? It means that about 0.632 or 63% of the variation in the number of Nobel laureates can be explained by the linear relationship between chocolate consumption and the number of Nobel laureates. This says about 37% of the variation cannot be explained by these chocolate consumption rates. Now there is a danger with correlation, and that's people assuming that correlation means causality, and that is not the case. As we've previously noted, there is a correlation between chocolate consumption in a country and the number of Nobel laureates coming from that country. That is ludicrous to think that eating more chocolate per capita makes its residents smarter, therefore more likely to win a Nobel Prize. There does seem to be a correlation, but that does not mean that they are caused or they are linked that way. There actually might be a third or a more underlying cause. 3 things that are very common errors when dealing with correlation is that we assume that correlation implies causality, and as we've stated, that is not the case. Second, we might be using data based on averages or means of the sample. That will also not be good for the correlation. And third is that we ignore the possibility of nonlinear relationships. I know we are not computing nonlinear relationships, but if we look at a correlation coefficient and say it's low, we might be tempted to say there is no correlation. And that is not the case. What R measures is the strength of a linear correlation. So having a low value for R means there is no linear correlation, and there could be another type of correlation. That's all we're going to cover from this section. Hopefully you found this helpful. I will speak to you next time.